kinetic energy. Guys also understand this symbol here? Greek letter sigma means sum. It's a math symbol. It's the Greek letter sigma. It means you sum up all the kinetic energies. That's what that means. And that's going to equal U, which is also going to equal N, which would be like the number of particles, how many molecules, how many atoms, etc., times a constant. This is a proportionality constant. We call it the Boltzmann constant. We don't have to worry what it is because we're not going to actually calculate that. Times T, which is temperature. So there is a relationship between temperature and the energy. Okay, but it's the number of particles times this proportionality constant, which is called a Boltzmann constant. It's a number that allows us, it's just like the universal gravitational constant. It's a constant that basically allows us to turn temperature into energy. All right. Now I'm going to show you this little video here, in a second. Now, what they are talking about is internal energy, even though they're going to call it heat in the video. They are really talking about internal energy. They're talking about how much heat can it give up, because they're going to pour this bucket of water into a pool, and they're talking about how much heat they can give up. So keep in mind, when they say heat, what they're really talking about is this, internal energy. All right, anybody need more time on this?
Eureka! The story so far. When the degree of hotness or temperature of something goes up, its molecules go faster and it expands. This expansion can therefore be used to measure temperature itself. A device which does this is called a hotness meter or thermometer. On the Celsius scale thermometer, the level to which mercury contracts at the freezing point of water is labeled 0 degrees Celsius, and the level to which mercury expands at the boiling point of water is labeled 100 degrees Celsius. And now, temperature versus heat. Here's a bucket of hot water at 50 degrees Celsius. And here's a cup of freshly boiled water at 100 degrees Celsius. In which of these two containers are the water molecules moving faster? The bucket or the cup? That's right, because the degree of hotness of the water in the cup is much higher than the degree of hotness of the water in the bucket. And the hotter something is, the faster its molecules move. Would you say, therefore, that there's more hotness in the cup than in the bucket? In that case, if the water in your swimming pool is just a bit too cold for you, you'd be better off emptying the cup full of boiling water into it, rather than the bucket full of water at the lower temperature, wouldn't you? Or would you? You don't seem so sure. Let's do an experiment to find out. Suppose you had two identical swimming pools, one yellow and one blue. And suppose that the water in both of them was just a bit too cold for you. When you pour the cup of boiling water into the yellow pool, does the water feel any warmer? You can hardly feel any difference at all, can you? Now pour the bucketful of 50-degree water into the blue pool. How does that feel? Quite a bit warmer? Aha! So even though the water in the cup was considerably hotter than the water in the bucket, the 50-degree bucket water is much better at heating up swimming pools than the 100-degree cup water. Why is this? Well, let's look at the facts. The bucket obviously contains many, many more water molecules than the cup does. The temperature of the average molecule in the bucket is 50 degrees, and the temperature of the average molecule in the cup is 100 degrees. Now let's substitute something else for the molecules. Imagine that instead of molecules, the cup were filled with $100 bills, and the bucket with $50 bills. Which would you rather have? Each individual bill in the cup is worth much more than each individual bill in the bucket. But the total amount of money in the bucket is much greater than the total amount of money in the cup. It's the same with hotness. The degree of hotness, like the value of the dollar bills, is higher in the cup. But the quantity of hotness, like the quantity of dollar bills, is greater in the bucket. We know that it's the speed of the molecules that determines the degree of hotness of something. In fact, degree of hotness only depends on speed. It has nothing to do with how many molecules there are. Although the molecules in the bucket aren't going as fast as in the cup, there are more of them, so they more than make up in mass what they lack in speed. And it's mass, combined with speed, that determines quantity of hotness. We've already seen that the word for degree of hotness is temperature. Now it's time to introduce the other word for quantity of hotness, which is heat. The big difference between temperature and heat is that temperature depends on speed only, whereas heat depends on both mass and speed. The water in the cup has got a high temperature, but very little heat. And the water in the bucket has got a much lower temperature, but a great deal of heat. Now you know why buckets of 50-degree water are better at heating up swimming pools than cups of boiling water. On the other hand, if you're looking for somewhere to dunk your tea bag...
Okay. So the idea here being they're talking about how much heat energy does it have to give up. What they're calling heat is really the internal energy. Bucket has more. Even though its individual average one molecule has less energy, has less average energy, but there are a lot more molecules. It's kind of like this idea. So you have an iceberg at 0 degrees Celsius, and you have a cup of coffee at 70 degrees. It's about what coffee comes out at, about 70 degrees, somewhere in there, 60 to 70 degrees. So I have a question. Temperature, average kinetic energy. Which one has greater average kinetic energy? Iceberg, coffee cup. Coffee cup. Coffee cup has a much greater average kinetic energy. Right? Remember, but how many molecules is temperature talking about? 1. 1. The average 1. The internal energy of the coffee and the iceberg, which has more internal energy. The iceberg has much more internal energy because it has much more mass. Much more mass on that. Now, if you had a coffee cup as big as an iceberg, coffee would have more internal energy. But if you just took your average little cup of coffee and an iceberg, the iceberg still you have lots more internal energy. Even though each individual atom has on the average much less energy, there's a whole lot more of them. That was the idea they were getting with the coffee cup, the little teacup, and the bucket. Like with the $50 bills. I can have a little teacup that has a few $100 bills, or I can have a bucket with a lot of $50 bills. Which are you going to choose? The bucket full of $50 bills, things like that. All right, that's it for today. Homework is chapter 21. So we're going to get a start on homework. Grab a book for your table. Yes, sir? Yes, you may. I will come around at the end. I will look to see whether we made progress. This is not a time they socialize. It's time to work on your homework. So each table can come get a book. Work on your notes on that. I will check to see you have actually accomplished something before the end of the period.